Hello and welcome back to CS103 Machines, Languages and Computation. In the lectures this week we're going to look at a puzzle that was set by Hofstadter in his book Gödelsche Bark. It actually introduces what's known as a formal system. And a formal system is where you have statements consisting of characters which have truth or falsity just based on the form of the statement. Let's see what this actually means. So you might remember, or you might not even, that in the first 5 weeks of this course, we're going to be looking at this proof that there are such things as non-computable functions, and we're building up to this. First of all, we've been looking at this word proof. And the MIU system, while it's not going to feel like proof, it's in fact going to be another example of doing proof. But this time it's proof in a formal system. What does that mean? Okay, so a formal system is one where we've got statements which are sequences of characters like this. X is equal to kx plus ky. That's the symbol s followed by this symbol, mean the two lines. Then you've got a k and an x, then you've got a plus symbol and a k and a y. It's just a sequence of symbols. And what we know in mathematics is that if we have this sequence of symbols, if that is a true statement, we know that this is also a true statement. In other words, we can rearrange it and use other symbols. So what we've actually done here is we've rewritten, as we say, this statement as this one. We've just rearranged symbols. We also have in our proofs more informal logical arguments, such as saying the smallest divisor of m must be prime. Well, mathematicians and computer scientists like it best if all of the steps of our proofs can be formal symbol manipulation. Then we can be absolutely sure that our proof is watertight. We're not relying on informal logical argument. So if we've got, say we've got some true statements, 2 plus 2 equals 4, for example. 5 is bigger than 3. If I've got some true statements consisting of symbols, and I've got some rules like this one up here that allow me to rewrite my true statements, then my proofs are cast iron guaranteed. And that could even, allow computers to construct proofs. And indeed, computer programs are written that construct proofs every day. And these things are called theorem provers. And we use them all the time, particularly in computer science in areas such as formal languages and in programming language theory. But in other areas as well, they're often used in AI too, artificial intelligence. So the second topic that I'm getting onto, the first topic was all about proof. Everything that you always wanted to know about proof, but were too ashamed to ask. The second topic is this MIU system, which is taken from Gödelsche Bark. And I'm going to provide you with chapter 1 of the book as a PDF, and you can read all about it. What he asks you to do is start with a thing called an axiom. An axiom is a statement whose truth you can just take for granted. See, it's one given to you for free. So in the MIU system, the only axiom that you have is MI. So MI initially is the only thing that you know to be true. So MI, M followed by an I, in that order, is a true statement. And what we've got to do is we've got to try to prove the theorem MU. And we're allowed to do that using 4 rules. These are the rules 1, 2, 3 and 4. The first rule, rule 1, says that if you have a string, any theorem that ends in an I, then you may add a U to it. So you can already see that if you start with mi as a true statement, the statement miu is also a true statement because you're allowed to add a u, and that also makes a true statement. So one way of making true statements is to find a true statement that ends in an I, and then you can add a u to it to make a new true statement. The old statement is still true, but now you've got another one. So you're building up a great big set of true statements, and that's what you're going to be doing. The second rule says that if you have any statement that begins with an M that is true, it's also true if you double what comes after the M. So if you've got MIU, then you can use the doubling rule, as I call it, to make MIU IU. You can double what comes after the M. The third rule, now the first two rules, as you can see, make longer strings. This one adds a U, and this one doubles what comes after the M. So they both make longer strings. The last two rules make the strings shorter. This one says that if you've got 3 I's somewhere in your string, you can replace those 3 I's with a U. So if you've got, say, M, 3 I's and a U, you could make, for example, MUU. We'll see this in an example in a minute. And then the final rule says that if you've got a string and you've got 2 U's in a row, then you may drop the 2 U's completely. So if you've got MUUI, then you could make MI, for example. So those are the 4 rules that you've been given. Add a U, double what comes after the M, 3 I's becomes a U, 2 U's can be dropped completely. Notice that they only go one way. You're not allowed to replace a U with 3 I's, only that way. Okay, so those are the rules. Hofstadter, in his book, he asks you, can you make MU starting from MI? That's his puzzle. That's the classical form of the puzzle. But I've got a different question for you to consider. I'm going to give you some arbitrary string as an input, and can you write a computer program for me to determine whether or not that's a theorem? So I'm going to put in some arbitrary string. I might put in the string MUIIU, and I want your computer program to tell me, yes, that's a theorem, or no, that's not a theorem. What if I put in the string IIMUU? Can you already see that that will be a theorem or not? What about if I put in the string XYZ? Is that a theorem? So you're already beginning to see, yes, I can decide whether or not some things are theorems or not. What I want is a computer program that says yes or no in a finite amount of time for any input. And that thing is called a decision procedure. We'll come on to that later on. But for the moment, let's focus on this thing that Hofstadter asked us rather than my version of the puzzle. Hofstadter says, starting from MI, can you make MU? So, what's a good way to approach MU? Well, the reasonable thing to do with it to start with is just by trying it out. See how it works. Have a mess about with it. So let's start by actually deriving a few theorems. So a derivation is the same thing as a proof. It's where we start with something that's true, in this case MI, and then we try to use forwards inference to prove things. So let's start by actually deriving a few theorems. So from MI, I'm allowed to use the doubling rule, that's rule 2, to make MII. from MII, I'm allowed to double it again and make M with 4 i's. So what I now know is that M2i's, that's a true statement, just like MI is. And M4i's, that's a true statement. So I now know that M1i, M with 1 i, M with 2 i's, and then M with 4 i's, all of those are true statements. And I can then use my rule number 3 to replace the 3 i's here in the string with a u. So MUI is also a true statement. So I've now got 4 true statements. MI, MII, M4i's and MUI. 4 true statements already. I can add a u to it now using my first rule. If the string ends in an I can add a u. And then finally I can double it. So I've doubled everything that comes after the M here to make MIU, UIU. At this point, you may be asking yourself, why am I doing this? Why am I messing about with this silly puzzle? Well, it's a very good example of a formal system. That's why we're messing around with this puzzle. When you learn propositional logic and other formal languages, they obey similar rules to this. But what I want you to do is to start by just starting with a language. This is a language which means absolutely nothing to you, so that you can get used to just manipulating the symbols. That's why it all looks a bit meaningless. But what I want you to know is that when I say these things are theorems, that means they are true statements. So MUI, UU, IU, that is a true statement in my language. And then finally, I can apply rule 4 to that, and I get to the true statement MUIIU. So that's true. So I've now proved that. That's a derivation. What I'd like you to do now is I'd like you to grab a piece of paper and try to derive for me this theorem. MUI, UIU. So MUI, UIU. And I'll give you the answer in the next video. For the moment, what I'll do is I'll go back on this and I'll leave you there. Those are the rules. So if you want to pause this video and jot down the rules now, that would be a good thing to do. So the statement that I want you to prove is MUI, UIU. Good luck, and I'll see you in the next video.